Fermat's last theorem. Why do cubes generate quadruples? C cubed equals A cubed plus B cubed plus D cubed. My motto? Plain honesty, simple truth, easy understanding. The joy of finding things out for yourself. The simpleton's mathematical coat of arms. In Euclid we trust. In 1 we have the normal polynomial equations resulting from the expansion of a plus b to the power n equal to 2 to 6. The coefficients of the equations result in Pascal's triangle. In 2 we see the polynomials that result from rearrangement of the equations to combine equal coefficients. 3. For the integers a plus b equals c, then a plus b cubed equals a cubed plus b cubed plus 3ab times a plus b, which becomes c cubed equals a cubed plus b cubed plus 3abc. It transpires that there is one composite 3abc that is equal to a cubic integer, and that is 3 times 1 times 8 times 9, which equals 3 times 72 is equal to 216 equals 6 cubed. We thus naturally form the cubic quadruple 9 cubed equals 8 cubed plus 6 cubed plus 1 cubed, and its infinite number of non-primitive quadruples. It does not, however, explain all the other quadruples. 4. Take the primitive Pythagorean triple 5 squared equals 4 squared plus 3 squared. Multiply through by 5 squared, then multiply through by 4 squared, then multiply through by 3 squared. In 2 we can replace the red items with their blue equivalents in 3 and 4 to give 5 squared equals 4 squared 4 squared plus 4 squared 3 squared plus 3 squared 4 squared plus 3 squared 3 squared, which simplifies to 5 squared all squared equals 4 squared all squared plus 2 times 3 squared 4 squared plus 3 squared all squared, alias a plus b all squared equals a squared plus 2ab plus b squared. Euclid's Elements, Book 2, Proposition 4. In 5 we treat the cubic quadruple 9 cube equals 8 cube plus 6 cube plus 1 cube, the same as the Pythagorean triple in 4, by omitting the 1 to form a triple, but then the two sides of the equality are no longer equal. We find numerically that the inequality is given by 729 squared minus 728 squared. In 6 we have repeated the exercise of 5 by omitting the 1 from the quadruple 12 cube equals 10 cube plus 9 cube minus 1 cube, and end up with the numerical inequality 1728 squared minus 1729 squared because of the omission. In 7 we have repeated what we did in 5, but this time on the whole quadruple, so that the two sides of the numerical equality are now equal. The additional terms obtained compared to 5 are, as one would expect, equal to the inequality found in 5. Repeating what we have just done in 7, for 12 cubed equals 10 cubed plus 9 cubed minus 1 cubed, we again find that the extra terms sum to the value of the inequality found in 6. To recap, we observe that the discrepancies in 5 and 6 equaled the sums of the additional terms in 7 and 8, thereby confirming the validity of the procedures. 10. Applying the methodology of 4, we see that a Pythagorean triple is elevated to a fourth power that, on converting into a second power, results in the binomial equation for the second power. Applying the same methodology in 5 to a truncated cubic quadruple, by admitting the 1 cube term, we unsurprisingly obtain an inequality between the two sides of the equation, the discrepancy being predictably calculable. The exercise was repeated on a second quadruple with the same outcome. Repeating the exercise on all 4 terms of the quadruples in 7 and 8 resulted in equality between inputs and outputs. The structure of the valid equation is similar in form to the a plus b all squared equation, but with the addition of 3 extra terms. 10. It is both self-evident and fact that all cubic quadruples can be derived numerically from the cubic equation that results from the expansion of a plus b all cubed, although not demonstrated here. 11. I have previously shown conclusively that a Fermat triple, if one existed, would behave identically to the Pythagorean triple in 4, and would generate the quadratic equation resulting from a plus b all squared, and would just be a clone, an absurdity. Likewise, a truncated cubic quadruple aspires to the same equation, but fails in part due to inequality between the two input terms whose a and b variables do not sum to the binary integer partition of the output term, an absolute must. 12. To conclude, it has been conclusively demonstrated that cubic quadruples are as much an integral part of the cubes as Pythagorean triples are of the squares, and that the concept of them or any higher power being compressed to form an all-integer triple is without any mathematical grounds, as substantiated by the complexity of the compacted binomial equations. In short, pursuit of the proof of Fermat's last theorem was, to say the least, just a fool's errand. 13. A consequence of the cubic quadruples are the following cubic identities. (14) In Diophantine analysis by Robert D. Carmichael in 1915, available as a free download from the Gutenberg project, in question 26 we find from 3 cubed plus 4 cubed plus 5 cubed equals 6 cubed, deduce 7 cubed plus 14 cubed plus 17 cubed equals 20 cubed. Answers please on a postcard that can then be pasted in comments, since nowhere in the article can I find out how it is done or deduced.